We have to find the voltages VA and VB, but we have not been clearly informed about which approach to adopt, whether to go for KVL or whether to go for KCL, whether to apply mesh, whether to apply the nodal analysis, right? So let us apply nodal analysis here because we are interested in finding the node voltage VA and we are interested in finding the node voltage VB. Right? So VA and VB voltages are not across certain resistor, but instead they are the voltages at a particular node of the circuit. Right? And hence what we can do is we can apply the nodal analysis here to find the voltages VA and VB. So this is how you need to first of all analyze which type of analysis is suitable for the given numerical or to the given problem of the circuit. Right, so what all this circuit comprises of? So it consists of independent sources 10 volt, it consists of independent sources 18 volt, there is one current source also of 1 by 3 ampere present in the network. Fine. So when you are going to apply the nodal analysis, the very first step is that you identify the nodes of the circuit. Right? So what are the different nodes of the circuit? So here the given problem already has mentioned as two nodes. Right? The node A and node B. Right? So these two nodes are already identified. Do I have more than other nodes other than this? Definitely not, because here comes the current source, right? And here the circuit terminates, right? So two nodes are sufficient here to analyze the complete given circuit, right? So where is the reference node other than these two nodes? Where is the reference node? Definitely the reference node is this node, right? Which is the ground of the particular network. So this becomes our reference node with which we will apply, with respect to which we will apply the nodal analysis to the node voltage, to the nodes VA and to the node VB. Okay, so with this we'll start with applying the nodal analysis to the given circuit. Right, now what was the steps that we have just seen? So we saw that we have done for the n nodes in the circuit, assign one node as the reference node. We have already done this. Assign the current. Now this is important. Now once we have decided the nodes A and node B, now the next step is to assign the currents. Right? How is that? What does KCL says? KCL says that the sum of incoming currents plus the sum of outgoing currents at a particular node of a circuit is 0, or algebraic sum of all the currents at a particular node is 0. That is what KCL says. Right, so for that I have to identify what are the incoming currents and outgoing currents. So here, to simplify that aspect, what we do is we assume that when we are going to apply KCL at a particular node, we will say that all the currents at this particular node are outgoing currents. We'll assume that all the currents at this particular node are outgoing currents, and that is what this particular point in the step says. Assign a current, right? You assign a particular direction of the current. So that's what we did. So to simplify the analysis, what we are going to assume? We are going to assume here that all the currents at this particular voltage, at this particular node, are outgoing currents. So with this assumption we proceed. Similar assumption we'll do here that all the currents with respect to node B are outgoing currents, right? So with this assumption we will now start to apply the nodal analysis. What is the next step now? The next step is to apply the KCL. So we'll apply KCL to node A. Now how do we apply KCL to node A? So what are the currents? Now first you identify what are the branches here which are um, coming at node A. What are the different branches? Okay, let us identify those branches. So there is a branch here. This is first branch. This is the second branch and this is the third branch. So there are total 3 branches with which we have to consider and apply the KCL at node A, considering these three branches. Right, so let us apply KCL at node A with respect to the first branch. Right, so here is my reference. Right, so VA minus the reference voltage, but there is one more voltage here, right? 10 volts in this particular branch. So how would you apply how would be the current which is flowing through this? So current flowing through this branch will be potential difference between these two voltages? Yes. So we have to take the potential difference between these two voltages. Right, so VA minus 10. Okay, we are applying indirectly, we are applying the Ohm's law. Right, so how would the equation of current be? We are applying KCL at node A. So we are interested in the current which is flowing in this particular branch. Right, I am interested in the current which is flowing. So how does the current flow in this branch? So current flows, that is because of the potential difference between the two ends. So here the potential difference will be VA minus 10, that will be the potential difference, divided by the resistor. V by R will be the current which is flowing in this particular branch. So what is the complete V? V is the potential difference between the two points, that is the node and the reference. So VA minus 10 upon 2 will be the current in this particular branch. Right, now this is first outgoing current. Now look at the second outgoing current. This is the second outgoing current. Right, so how is the current flowing in this? So it is definitely the potential difference between the node voltage VA and the reference voltage. The reference voltage is 0. So simply it becomes VA minus 0 upon 10, which is simply VA upon 10 is the current which is flowing in this particular branch. Right? Then comes the third branch, this branch. So what is the potential difference here? So it is VA and VB. These are the two potentials. So take the difference. So VA minus VB upon 5 will be the current which flows through this particular branch. So I now know the currents in all the three branches. Now what does KCL says? KCL says the algebraic sum of all these currents. So what I should do to all these currents? I should add it. Right, so I should add all these currents. So what happens now? How is my particular equation? Right, so as we just discussed, what was the first equation? VA minus 10 by 2. So you could see here the first term is VA minus 10 by 2. Right, what is the second equation? It is VA by 10. VA minus 0 it is. So instead of that, we can directly write VA by 10 is the second current through the second branch. And the third branch is this. So potential difference is VA minus VB upon 5. Right. And what does the KCL says? Algebraic sum of all these currents. So we are adding all these currents is equal to 0. Algebraic sum of all the currents is 0. Right. So this is how we applied KCL to the node A. Okay. We applied KCL to this particular node A. Right. Now what you need to do is simplify this. Okay. Now let me talk about the next node VB. Okay. How would you let me give you a minute. You try this. You try with applying KCL to particular node VB. So as just discussed, identify all the branches first. So what are the branches here? Right, this is the first branch. Right, this is the second branch. This is the third branch. And then this is the fourth branch. So there are total 4 branches that we have to consider when we apply KCL to node B. There are total 4 branches. So let us start with the very first branch. So now I'm interested in the current which flows from node B to the other end, that is my reference. So I'm talking about the current which flows from node B, right? So we have assumed what? We have assumed that all the currents are outgoing currents, right? So when we assume that all the currents are outgoing currents, who is at a higher potential? Definitely It is the potential at point B which is at higher potential, right? So when current flows in this direction, it means that current flows from a higher potential to a lower potential, correct? So it means that potential at point B is at higher potential than with respect to the potential at point A. And therefore, how would we write the current in this particular branch? So higher potential minus lower potential, that is VB minus VA upon 5, right? So this will be the current in this particular branch. Now talk about this branch, right? So it will be potential difference again. So VB minus, here is a reference potential which is at 0. So simply VB upon 15 would be the current in this particular branch, right? Now when I come to this particular branch, here there is directly a current source which is outgoing current source. It means that it is coming from node B and going to the reference, right? So since it's an outgoing current, we will directly consider it as plus 1 by 3 in the equation, right? So current, this is the current that we need to add since it's a outgoing current. And then finally the fourth current which flows from the node B through 3 ohm resistor through the 18 ohm independent source to the reference node. So how it will be? We have to do the potential difference here. So what is the potential difference? So VB minus 18 divided by 3 would be the current that flows through this particular branch. So this way you identified all the currents. Now what does KCL says? Algebraic sum of all these currents should be 0. Right, so if I apply the definition of KCL, right, what is the equation we get? We get, let us identify once again. So VB minus VA upon 5, right? So you could see here VB minus VA upon 5 is the first branch. Now this particular branch is VB by 15, correct? The third branch is the only current source, and since it is outgoing, right, we need to add it. It's 1 by 3, and then the final current VB minus 18 by 3. So VB minus 18 by 3, and algebraic sum of all these currents is 0. So we have added all these currents and it is 0. Right, so now we have two equations of VA and VB, right? So you get two simultaneous equations. So when you simplify the first equation, you get this, and when you simplify the second equation, you get this, correct? Now we need to solve VA and VB, and this is what you get when you solve VA and VB. So what I would like you to do is to just note down the circuit, and I hope you're doing that along with what we are discussing, right? So you're noting down all the things. So maybe the time may not be sufficient for you to solve the simultaneous equations, but that you can do as a part of homework and verify your answers, whether you get VA to be 9.39 and VB to be 12.58 respectively. Okay, so that part you can do as a part of a homework. What is essential is to understand the KVL, the KCL equations at the nodes, right? Let's move on to the next question, right? So here, first of all, carefully analyze what is the question all about. Understand the question properly. So here is a circuit given to you, and you have been asked to find VA, VB and VC voltages. So analyze the given circuit carefully. See what all are the sources involved in the given network. Where are your VA, VB and VC voltages, right? And in what way, what steps will you do to find these voltages VA, VB and VC? So VA, VB and VC are mentioned in the given circuit. So this is your voltage VA. This is your node A where you are going to find your voltage VA. This is another node where you are going to find the voltage VB. And this is the third node where you are going to find the voltage VC. So you have been given 3 nodes and you have been asked to find these node voltages. Right? What does the circuit comprises of? The circuit comprises of an independent source, 2 volts. Uh, what is this? The first one is the current source, right? It's an independent current source. But what is this? This is a dependent current source, right? This is what you have to carefully and identify, right? The arrow will tell you that it's a current source, right? So it's a dependent current source, right? And what type of current source is it? Is it current controlled or voltage controlled? So this particular associated parameter will help you to identify whether it is a dependent current, whether it is a current controlled current source or voltage controlled current source. So here the parameter is 2I1, and that's what tells us that this is a current controlled current source, right? So this way first you analyze. So somewhere I must have I1 in the network, right? So here I1 is shown to you. So I1 is the current through 2 ohm resistor, right? So if there is a dependent source involved, right, the dependent parameter must be present in the circuit, right? So I1 must be part of the circuit. So I1 is shown here, which is the current through the 2 ohm resistor, right? So this is what is your given network, and you have been asked to find the node voltages VA, VB and VC respectively, right? Okay, so which type of analysis would you select here? Since VA, VB, VC are the node voltages, nodal analysis would be a much better way of finding the node voltages, right? So hence we'll do the nodal analysis, right? So what are the steps? Identify the nodes. Now these nodes are already identified for us, right? These node voltages are already been identified in the given problem statement itself. So one of the steps is reduced, right? So we did not identify the node. So our reference node will definitely be this, right? The ground of the network. This will be a reference node, right? And as just discussed, whenever we apply KCL to a particular node, we will assume that all the currents are outgoing currents, right? So it means that the node at which we are going to apply KCL is at a higher potential, and that's why all the currents are the outgoing currents, correct? Okay, now let us apply the node KCL to one of the nodes. So let us apply KCL to node A. So when you are going to apply KCL to a particular node, identify all the possible branches. So what are the possible branches with respect to this node? So this is the first branch. This will be the second branch. This will be the third branch. Is it over? No, there is one more branch here, correct? So there are total 4 branches. So what is important, that is to first identify all the possible branches at that particular node, right? So this is the first branch, this is the second, this is the third, and this is the fourth branch, right? Now we will start to apply the KCL at node A. Right. So we have assumed what? That all the currents are outgoing currents. So look at the first one now. What is it? It's a current source, right? And the current is inward current. What we have assumed at this particular node, that all the currents are outgoing currents, whereas this current is incoming current. It means that it is in a direction which is opposite to our assumption, and hence when we consider this 4 amperes, we should give this 4 amperes as a minus sign, right? So I should consider, as this is incoming current, because we have assumed that at this particular node all the currents are outgoing currents. So with respect to the current direction, we have assumed this current source is having a direction which is opposite, and hence when we are formulating the equation, what we understand is we have to consider a minus sign to this particular current source. So the very first equation is minus 4, correct? plus. Now we'll go to the next current. Now we'll consider the current in this branch. So potential difference will be VA minus 0, that is the reference potential. So VA upon 1 will be the second equation, right? Third would be this branch. Let us consider this branch. So what is the potential difference here? VA minus VB, but that's not the only thing. There's one independent source also, right? There is one independent source also. So what will be the total potential difference then? VA minus 2 minus VB upon 2, right? What will be the total potential difference between these 2 points? It will be VA minus 2 minus VB is the total potential difference divided by the resistance of the path which is 2. So VA minus 2 minus VB upon 2 will be the current in this particular branch. And the final current will be the current which flows in this direction. What is the potential difference here? VA minus VC. So potential difference is VA minus VC upon 2. So there are total 4 currents that we need to consider. Now you verify what has been done here. Correct? So let's verify. So we started with this particular current in this particular branch. So since this is incoming current, we consider it to be minus 4. Then we took VA upon 1, right? Then the next current was this in this particular branch. So how did we do it? VA minus 2 minus VB upon 2. This is the third current, and the fourth current was this. So VA minus VC by 2. Right? So these are all the currents. Algebraic sum of all these currents is 0. Right? So you got the equation that applying KCL to the particular node A. Right? Similarly, now we have to apply KCL to the remaining 2 nodes. So let us apply KCL to node B now. Right? Apply KCL to node B. What you need to do, as just discussed, we have to identify all the branches. So identify the branches. So this is the first branch, this is the second branch, and this is the third branch. So only 3 branches are there when we consider node B. Right? We have only 3 branches. So let us start with applying KCL to node B. Right? So try to formulate the equation for this particular branch. So it is going to be the potential difference. So since the current is outgoing current, it means that the potential at point B is higher potential. So VB minus VA will be there. What about this particular source? Right, look at the terminal now. Now the terminal is negative followed by positive. So it's going to be rise in the potential. And hence I need to add this particular voltage when I am considering current in this direction. Correct? So the equation turns out to be VB plus 2 minus VA upon 2. This is what will be the equation of this particular branch, right? Because the polarity of this particular voltage source is opposite to what we were considering earlier, right? So now we are going from negative terminal to positive terminal, right? And hence it is to be considered as the rise in the potential, and hence it has to be added. So it will be VA plus 2 minus VB plus 2 minus VA divided by 2 will be the current in this particular branch. Now come to this branch. What we have assumed that we have an outgoing current, right? But what about this particular current? It is incoming current. It means that when we consider this, we have to negate it. So what will be the current here? It will be minus 2I1. This is what I have to consider when I am considering. This will be the current which I have to consider when I am talking about this particular branch. And then the third current is this. So potential difference is VB minus VC by 3. is the potential difference between the two, VB minus VC, divided by the resistance of the path, that is 3. So these are the currents. So algebraic sum of all of them will give you the equation for that particular node. So let us verify it. Correct? So how we got the equation for the first branch? So it was VB plus 2 minus VA by 2. So this is the first, right? And then we consider this. So since this is an incoming current, we have to consider it as minus 2I1, right? And then the third current, VB minus VC by 3, right, is the third current. And we added all of them and this is 0, correct? So this is the particular KCL applied to node B, okay? Now what you need to do is simplify. There's one more node yet which we have to consider, yes. But we can start to simplify these two. Simplify the equations. Now for simplification, there's one more thing which is being done here is I1, right? Because the equations are in terms of voltages. So we need to put this I1 again in the form of some voltage. Now how is I1? I1 is having this direction. It means that it flows from a higher potential to a lower potential. So I1 will be the difference of VB minus VC by 2. Since I1 is given in this particular direction, it means that VA is at a higher potential than with respect to VC. So I1 equation will be VA minus VC by 2. So that's what is I1. So we'll put this I1 in the equation so that we have all the terms in, we have all the equations in the form of VA, VB and VC. Right, so we substituted I1 here and we got the equation in terms of VA, VB and VC. Right, so we are going to simplify it and we got the equations 1 and 2, which are functions of VA, VB and VC by solving the equations, KCL equations applied to node A and node B. Right, so we have got two equations which are functions of VA, VB and VC. Right, but the problem is not yet over. We have one more node to go. So now let us apply KCL to node C. We'll apply KCL to node C. Right, so once again identify all the branches which are possible with respect to node C. So this is the first branch, this is the second branch and this is the third branch. Right, so these are the three branches which we need to consider when I apply node KCL at node C. Right, so let us start with the first branch now. Right, so as usual we assume that all the currents are outgoing currents, right? So this particular current which flows in this particular direction will be the potential at the potential difference. So VC minus VB by 3. Then current in this branch will be VC minus the reference potential which is nothing but 0. So VC minus 0 by 5 which is nothing but VC by 5. And the third current which is VC minus VA by 2. Correct? VC minus VA by the resistance of the path which is 2. Right? And algebraic sum of all these three gives me the complete equation applied at node C. So let us verify it here. So verify that what we have just discussed is correct. So look at your first equation, first path. So VC minus VB, correct? VC minus VB by 3, the first path, it is this. Now second path here, VC by 5. And the third path, VC minus VA by 2, right? So VC minus VA by 2, right? And sum of all these is equal to 0, right? So when you simplify this, you get one more equation in your set, which is again a function of VA, VB and VC. So we'll call this as equation number 3. So 3 node voltages we had formulated has given us 3 different equations which are functions of VA, VB and VC. Now the thing is, how do we solve? Because there are three terms involved here. If it would have been two terms, we could have solved by usual simultaneous equations, right? When three terms are involved, the things become complex, right? So at that time, how do we proceed? We proceed by applying the Cramer's rule, right? We proceed by applying the Cramer's rule. Now how do we apply Cramer's rule? So for that, we'll first of all express the equations 1, 2 and 3 in a matrix form. Right? We'll express equations 1, 2 and 3 in a matrix form. So see how it has been done here. So you have the equations 1, 2 and 3. So start with equation 1. So what are the coefficients here? The coefficients are 4, minus 1, minus 1. So write the first values of the coefficients from equation 1. 4, minus 1, minus 1. Right? Now look at your second equation. What are the coefficients here? The coefficients here are minus 9, 5 and 4. So that becomes the second row of the matrix. Minus 9, 5, 4. Whereas what are the third? From the third equation you get the third coefficients, right? Which is minus 1 by 2, minus 1 by 3 and 31 by 30. Right? So I have put it in the third row of the matrix. Right? Close your matrix. Right? So this matrix belongs to which variables? VA, VB, VC equated to. So now what we write in this particular column are the right hand side of these equations, right? So it is 10, minus 6 and 0. So 10, minus 6 and 0. So this is how you formulate the given expressions in the form of a matrix. Now you apply the Cramer's rule. So what the Cramer's rule says? So the Cramer, you already know this, but I'll just quickly tell you how do you solve the Cramer's rule. So you form the determinant of the matrix. So this particular matrix is taken as it is in the denominator, whereas in the numerator, when we are finding the value for VA, replace the first column by the coefficients on the other hand, right? Your coefficients here are 10, minus 6 and 0. So replace the first row by 10, minus 6 and 0. So replace it by 10, minus 6 and 0, keeping the remaining coefficients of the matrix as it is. Right? So when you're finding VA, you're going to replace the first column. Right? So I replace the first column with the constants 10, minus 6 and 0. Right, and now find the determinant. So we are finding the determinant of the upper matrix of the lower matrix, and when we solve it and divide, you get the value 4.30. Correct? Complete analysis has been done for you. Those who face a difficulty, the complete analysis is shown to you. Mathematical evaluation has been done for you. Right. How do you find VB now? How do you find the next coefficient VB? So for VB, you take the matrix again, but this time for VB, replace the middle column by the coefficients 10, minus 6 and 0. Keep rest of the matrix elements as it is. So I am going to replace this middle column by 10, minus 6 and 0. So you could see here how we have formulated the equation for VA. So for VA, when we have written the equation for VA, we have considered 4 minus 9 1 by 2 as it is, whereas what we have done to the middle column is we have replaced middle column by the coefficients 10, minus 6 and 0, whereas the third column is as it is. What about the denominator? The denominator remains the same, remains unchanged. Right? So denominator is the entire matrix is as it is. Right? So now you find the determinant of this. So find the determinant of the numerator. Denominator, it's what already you have done in the previous step. So you already have the value of it. So find the determinant of the numerator, divide it, you get the value for the voltage VB. Similarly for VC, what you need to do now? Keep the first two rows as it is. whereas replace the third row by the elements 10, minus 6 and 0. So your matrix is first with first two elements as it is, whereas the third is replaced by 10, minus 6 and 0. Right, so that's what we did here. We replace the third column by 10, minus 6 and 0, keeping the first two elements as it is. Right, your lower matrix is as it is, the entire matrix, so divide it, you get the third value VC. So this is how you can use Cramer's rule to simplify your given simultaneous equations. So when there are more terms involved, you can use this particular Cramer's rule and get the values VA, VB and VC. Right, so this is how we simplified the given network element.